I'll now hand off the microphone to Professor Boyd, who will introduce the next speaker.
Okay, well, hello, everybody. Let me start off by thanking Professor Steinberg for that great talk they just gave us. But we have another great talk coming up. It's from Dr. Nick Vamivakas from the University of Rochester. So let me tell you a little bit about his history. He studied electrical engineering at Boston University and received his PhD from there. During his thesis work, he developed high-resolution microscopy and spectroscopy techniques to study the electro-optic properties of specific nanostructures. He was then a postdoc at the Cavendish Lab at the University of Cambridge. And finally, he joined the faculty of the University of Rochester Institute of Optics in 2011, and he is currently an associate professor. His research centers on light-matter interaction at the nanoscale, and he is particularly interested in using optics to interrogate and control both artificial and naturally occurring solid-state quantum emitters. So I think that's enough. There's enough talking for me. Let me turn over the stage to Nick.
Okay, thank you, Bob, for that kind introduction. And let me get my slides up here. I'm really excited to be able to share with you today some of the work that's going on in my lab related to actually optical coherence. It is a shame that we can't be doing this together in Ottawa and have to do this remotely, but I do look forward to being able to visit there in the very near future. What I'm going to talk to you about today, or before I get started with what I want to tell you about today, I do want to recognize, just as our previous speaker has said, you know, these experiments and research is not done by a single individual, and I've been really fortunate to work with a fantastic team since I've been here at the Institute of Optics in Rochester. A number of students have contributed to the work I'm going to share. In particular, Wadud has been really instrumental in a lot of what I'm going to tell you about. There's been two talented postdocs, Xiaofeng and Kevin. Both contributed in various ways to this effort, and both have fortunately gone on to faculty positions within the last year. And then I have a number of fantastic faculty colleagues at the Institute who have, you know, I've had many stimulating discussions about the work that I'm about to describe. And of course, none of this would be possible if it wasn't for the generous support of a number of federal funding agencies, as well as the University of Rochester. So to provide a little bit of context for this discussion, I'm going to remind you about something probably most of you don't need much reminding about, and that is one of the crowning intellectual achievements of 20th century physics, that being the discovery of quantum mechanics. Right, it forced us to really reconceive how we understand and think about the natural world. And as we built up the mathematical machinery to deal with quantum mechanical systems, some interesting properties began to reveal themselves. Amongst those, quantum entanglement was discovered in states of quantum systems which could have or exhibit correlations that were sort of perplexing from a classical physics perspective initially. And with that discovery, it was a short time later where we recognized that entanglement, although maybe a little bit mysterious physically, could also be used as a resource to empower quantum information science. And so right now, entanglement rears its head in everything things related to quantum communication, quantum computing, quantum sensing. And so it really is a valuable resource in quantum information science. Now, in parallel to this development, maybe a little less well known, but equally important in my eyes, was really a really great leap forward in electricity and magnetism, and specifically the discovery of optical coherence, where we formalized or figured out how we could ask questions related to basically how much are electromagnetic fields like themselves. And that's in some sense the essence of optical coherence. And of course, these developments in optics fed into the quantum theory of light. And quantum optical coherence was sort of the window that many of these properties related to entanglement or other interesting features predicted by quantum mechanics could be probed. We heard the previous speaker explained in great detail how quantum optics provides a window into understanding tunneling time. Now, what we have been looking at recently in my lab is it possible to use some of the tools that have been developed in quantum information science, and can we bring these back into classical optics? The idea being that there might be an opportunity to discover new approaches to make more empowered optical technology. Equally attractive is the possibility that quantum information science might teach us new things about classical optics that we wouldn't recognize if we weren't to use these tools. So the way that this whole research program gets kicked off is we go back to the electric field vector of an electromagnetic beam and express it in a slightly more cumbersome notation than we might find in an Optics 101 textbook. But the point of this reconception of the electromagnetic field, in particular electric field vector, is we've made explicit here the different degrees of freedom associated with this beam assumed to be propagating along the z direction. And with each one of these degrees of freedom now, we have mode functions to help us characterize the degree of freedom. And by doing this, we can now express the electric field vector as a vector in a multi-dimensional vector space. Right? And once we have done this, we make kind of an analogy to a vector in a Hilbert space, where the different degrees of freedom now represent different vector space dimensions. And once we have done that, we've organized our electric field in this capacity, right? Recognizing the spin and the spatial degrees of freedom and the temporal degrees of freedom. It's now possible to take tools of quantum mechanics and quantum information science and bring them to bear on classical optics. And I'm not going to go too much into how we have done that, just to maybe give you a sense of the kinds of understanding that it does provide, is that for someone who's schooled in quantum mechanics or quantum optics of multipartite systems, one knows that when you have a bipartite system that's in a pure state and you look at one of the subspaces of that system, it will appear to be completely incoherent. And so that kind of thinking also applies in classical optics. You can have beams that have correlations so that if you look at a particular feature of the beam, it appears to lack any coherence. And this is a bit surprising since lack of coherence in optical beams tends to be ascribed to uncertainty in the source that has generated the beam. So recognizing that correlation actually can lead to apparent lack of coherence is an insight that quantum information science has given back to classical optics by applying some of the tools back in this realm. Now, critical to this program is being able to measure the different degrees of freedom associated with our beams and fields. And one specific challenge that we have been dealing with for some time is how one might take the spatial structure of a beam and break it into some constituent set of spatial modes. So if you like, we would love to have a grating. We can illuminate with one of our beams and flying off in different directions with the different spatial modes that go into comprising that beam. So we don't exactly have a grating to do that. What we did do is we've built an interferometer that allows us to analyze the spatial structure of our beam. This could be a whole talk in itself, but the essence of this device is we have an input to this Michelson interferometer. And what we want to do is understand, in this example, how to decompose this particular input into a collection of Hermite-Gauss modes. I'll say why that is interesting in a few more slides. And so to do this, what we need to do is we need to introduce a delay line that is not an ordinary temporal delay line, but we introduce a different optical transformation, in this case, the fractional Fourier transform. And the fractional Fourier transform has two knobs that we can turn to tune the order of that particular optical transformation. And so now why the fractional Fourier transform is important in this context is that the Hermite-Gauss functions are eigenfunctions of that particular transformation. And so when one of these eigenfunctions passes through this optical transformation, it gets a mode-specific phase associated with it. And so now if I put this input into my Michelson, one half of the beam propagates through my fractional Fourier transform, the other part of the beam goes off the reference mirror. When I bring these two beams back together and they homodyne against one another, each mode interferes with itself with a phase that's determined by the fractional Fourier transform. The interferogram that I get at the output in this case will be two-dimensional. And if I then take the Fourier transform of that interferogram, I can figure out which spatial modes or which Hermite-Gauss modes were active in my input. And so the essence of an interferometer is you're able to discover the eigenfunctions in your input that are the eigenfunctions of the delay line you have in your interferometer. One interesting note is that this really doesn't, this is a sort of basis independent device. What I mean by that is you give me an optical delay line and I can analyze it into its eigenfunctions. The interferograms will all look the same, but what it really is critical is that the delay line that you've put into your interferometer, and that's what is the window into the eigenfunctions that are present in the Fourier transform of your interferogram. And so here is just some data demonstrating this in fact works. Here we've put in a 2-2 Hermite-Gauss mode, a 4-1, and then a superposition. We've created the interferograms that I just described, and through Fourier analysis have been able to determine which modes are present in the input. Now, the same kind of black box can also analyze the parity of the beam. And so why this particular tool is interesting for us is that being able to now measure the spatial mode structure of a beam actually has some application in quantum limited advanced scene characterization. And so here, what I'm next going to describe is a way we can use classical optics to characterize scenes and extract or estimate parameters that we know quantum mechanically we couldn't do any better in our estimation task. And so to remind you, in the context of incoherent direct imaging, there is this Rayleigh limit. If you have a point source and a finite size aperture and you know the wavelength of that source, your image is going to blur out. And then if you have 2 point sources and you would like to determine their separation, of course, this blurring gets in the way of your ability to determine that separation. And the Rayleigh limit is just one of a handful of resolution criteria that tells you essentially when you can or when you cannot resolve features in your source or object plane. And so not so long ago, a number of groups kind of catalyzed by Mankay-Tseng asked the question, what does quantum measurement have to say about resolution? And resolution and resolvability really turned into a parameter estimation problem. And so the way that this works, I want to first remind you of some tools from Fischer information. And basically these are
Vamivakas, we've lost you. Are you there? We have a temporary issue here. Or do we have any questions from the audience coming up?
I apologize. Am I back on now?
Yes, sir, you are.
Yeah, I apologize. I somehow got kicked off. Okay, so where we were, parameter estimation relies on the Fischer information, and the Fischer information of a given measurement approach, and there are 2 illustrated over here, basically specifies the likelihood function, and then you turn the crank on that likelihood function to figure out your Fischer information for a given system architecture. And the inverse of that Fischer information bounds the best you can do in determining the variance. And this is called in parameter estimation the Kramer-Rao bound. Now, what was interesting and what Mankay looked into was the so-called quantum Fischer information. And so what's distinct from the classical Fischer information is that the quantum Fischer information describes the maximum amount of information we can distill out of a scene. And it is basically measurement independent. It doesn't depend on a specific measurement scheme. Now, just like any limit, the challenge is up to us to identify a measurement scheme that can then achieve this quantum limit. And so illustrating here, a comparison of two different Fischer information calculations. What we're looking at here now is a function of the separation of our two sources. We've calculated the, well, actually this was reported in this paper, but we've also calculated similar curves where we're looking as the separation between your two sources goes to 0, the direct imaging Fischer information goes to 0. What that means is you're not able to reliably estimate the separation of your 2 point sources. This was called Rayleigh's curse in the literature when it was first discovered. In contrast, what is interesting in trying to estimate the separation of your 2 point sources, the quantum Fischer information tells us that there should not be any change in our ability to distill information out of our scene. So we should be able to make the same estimate of separation regardless of how close or far apart the 2 point sources are. And this can be contrasted with the Rayleigh limited resolution of an imaging system, whereas the sources get too close to one another, they begin to blur out and they can no longer be resolved. Now, what was nice in Mankay's paper is they gave a prescription for how one would do this. To do this, you take the received optical energy on your image plane and you decompose this into a collection of Gauss functions or a collection of different spatial modes. And then by measuring the coefficients in this decomposition, you could then estimate the separation between your 2 point sources. So what's nice here is SPADE turns out is a completely classical measurement, but if done right, we can achieve the quantum limit for determining the separation of these two incoherent point sources. So some of the infrastructure that we had to develop to be able to navigate the different degrees of freedom of an electromagnetic beam allows us to immediately address problems related to localization of point sources in an optical imaging system. Now, we weren't the first group to do experiments in this space. In fact, our previous speaker did one of the pioneering experiments for localizing incoherent point sources. And these are the kind of data sets that come out of these experiments. You see your estimate of the mean square error on your separation. This is the Kramer-Rao bound for direct imaging. This is the quantum limited Kramer-Rao bound. And again, these are all as a function of the separation of your 2 point sources. And the important point in this data set is these blue crosses here, where you see as the point sources get closer together, they are following the quantum Kramer-Rao bound and they're not diverging as one would expect for a direct imaging system. The inset of this figure panel shows the actual estimate of the separation of the 2 sources in the region inside of below 1 indicates separations that are within the Rayleigh limited resolution. So here is an example of advanced scene characterization for incoherent point sources. We're using ideas of basically quantum measurement. You're able to make classical instruments that can outperform conventional imaging technology. What we were interested in was what role coherence or partial coherence has to play in this same kind of problem. And so this is some of the maths behind that. The sort of important point is this equation right here, this classical interference equation, may be written a little obscure, but here there are the terms related to the energy that's delivered to your object plane from the 2 sources as if they were incoherent. And then this cross term here is governed by how correlated the sources are. And what's interesting is a function of this correlation, the structure of the optical energy that you receive on your detector can change quite dramatically. And so we were interested in what role this coherence parameter plays in your ability to localize these 2 sources. And so the first thing we wanted to make sure was that if we looked at the direct imaging case and we looked at the Fischer information, that there is the separation between the sources went to 0. All right, it was impossible to localize or to determine the separation. And here now there are a number of curves. Each one of these curves are determined by or are governed by the degree of correlation between our 2 sources. They can be completely correlated all the way to completely uncorrelated with completely incoherent in between. And so again, the fact that all of these curves go to 0 are indicative that there is in fact there is a Raleigh's curse at play here when you're trying to directly image partially coherent point sources. Now, the next thing I guess the other tidbit of information that was interesting for us as we were setting these experiments up, there was a little bit of a controversy that was brewing in the literature related to what role partial coherence does play in estimating the position of two partially coherent point sources. And so on the left, what I'm showing you is some predictions from Mankay Sang's group, and on the right, similar predictions from Baha Saleh's group. And these are the fission information curves for the same degrees of correlation. Now we're not thinking about sorting into Hermite-Gauss modes, we're actually sorting into even and odd or parity sorting the received optical energy. And so there's clearly a difference between these two curves. And so as we were setting these experiments up, we realized we needed to get to the bottom of this difference if we were going to have any success in carrying out the experiments that we were setting up. And so what we realized in looking through these is that one really needs to be careful about apertures in your optical system, as well as what you know and what you don't know in the particular problem that you're tackling. And so first, let me explain to you how partial coherence can influence the amount of light you receive on your detector plane. And have in mind, in the upper corner here is a 4F system. And what I'm doing is introducing just a soft Gaussian aperture in the Fourier plane. And these three plots through the middle of the slide are for two different degrees of partial coherence. The first plot is for incoherent sources. The second and third plot assume a fairly large degree of anti-correlation between the two sources. And what's different between plot 2 and plot 3 is just the separation between the sources. Now, for an incoherent source over here on the left, regardless of the separation, if I have an aperture on my Fourier plane, I'm going to always receive the same amount of energy on my detector plane. This doesn't vary for any of my separations. Now, interestingly, for partially coherent sources, depending on their separation, the amount of light that will make it to my detector is determined by how separated the two sources are. In fact, you can show that the image plane photon number scales with separation as well as the degree of coherence. And so that was important. So what that meant was that photon number is critical to understanding, resolving or localizing partially coherent sources. And in fact, their distinction between the Sang and Sala predictions, and in subsequent to that, there was another group that got into the theoretical discussion about this problem. And what ultimately was revealed is that what we know about photon number is critical for the Sang-Nair approach. You assume you know your photon number and your source, and you don't know your separation, and you do know your degree of coherence, and that's a one parameter estimation problem. For these other two plots, what's critical is that now you don't know your photon number, and where you don't know it is also of interest. So in the middle plot here, we assume we don't know our photon number in our object plane, and then to recover the results on the right, we assume we don't know our photon number on our detector plane, as well as in both of these two cases, you don't know the separation of the sources. So again, what you assume you know is critical for what you can estimate in trying to, and if you'd like to estimate the separation of these two partially coherent sources, then you need to make a statement about what you do or don't know about your photon number. Now, in an experiment, we typically only have access to the image plane photons, and this is like a situation that you encounter in microscopy as well as in imaging. And so the way that you do this operationally, again, thinking in the context of parity sorting, is we measure the even, we measure the odd photons that we're receiving, we divide by the total number of photons we receive to build up our probability distribution that can then be related to our likelihood function. And then turning the crank, we're able to figure out the Fischer information. And we do this just right now. I'm showing you both experiments and theory related to this exact problem. On the left are our estimates, our maximum likelihood estimates of the shift between our two partially coherent sources. Each one of these data points is what we would call sub-Rayleigh, meaning we are doing this better than one would predict by the Rayleigh limit. Also of interest is that the anti-correlated case is giving us a better estimate in the shift. And that jives also with the fact, if we were to look back at the Fischer information curves, we're acquiring a bit more information when we're making measurements when the sources are anti-correlated. And on the right here is again showing that we are nearly achieving the quantum Kramer-Rao bound. And that depends again, each one of these curves are for there's the incoherent curve here. This is the theory, and this is our collected data. And the lower curve here is again that anti-correlated case. And you're seeing again, these are all separations that are within the Rayleigh limit of our direct imaging system. what that taught us was that, parameters that the parameters that you need to estimate are important in your estimation problem. It's kind of like a tautology. So we started thinking about, what parameters are or could be active in a localization experiment. And so we looked to, so we went to extend the sort of simple 2-point problem to giving, taking or having lack of knowledge not only about the separation between the two sources, but also the complete degree of coherence. So here, what I'm illustrating for you is the sort of disk of coherence or coherence disk. And you can imagine in this kind of estimation problem that you have no knowledge of the complex degree of coherence. So that was another pair of parameters we put into our theory. And then we also considered cases where you didn't know the energy of the two sources. So maybe they were no longer equiamplitude. All right. And doing this ultimately multi-parameter estimation, we were then able to make predictions. And so these plots are a little busier. What they are is, as you walk longitudinally, each one of these points represents a particular shift between your two sources. And then this disk is the Fischer, quantum Fischer information. As in this case, we assume that we know the coherence phase, but we don't know the magnitude of the coherence. So we know the angle, but we don't know the length over here. And then we plot the quantum Fischer information. And what this reveals already with these two parameters is the ability to distill information out of your scene very much depends on the orientation of that complex degree of coherence. And there are regions, the red I want to draw your eyes to, because the red are all locations where the quantum Fischer information is 0. And these are places where the Rayleigh curse kind of resurges. Now, if all of these parameters are unknown, and then we want to make a statement about the separation, this lower plot basically illustrates all bets are off, and that as soon as you have too many parameters that you need to estimate, you're no longer able to do better than one might do with a direct imaging system if you want to try to tease out the separation of two partially coherent point sources. All right. So with that, I think I will, I did tell you a little bit about how quantum information science can lead to new approaches for enhanced optical technology. I do see our time is winding down. So I'm going to jump through a bit. We've done some work where this type of thinking has now fed back into quantum optics. And since I see my time is done, I will just jump to the last slide. And I like to leave this quote when I finish talks on coherence. This is from Professor Wolf's Ives Medal address. Subjects that often appear to be well understood and perhaps even a little old-fashioned have frequently some surprises in store for us. And so this journey of using quantum information science and optical coherence has been pretty fruitful, and there's a lot of new things we've learned, and I hope just shared one facet of this with you all today. So I'm happy to, I appreciate your attention and happy to take any questions that we might have.
Okay, thank you for your presentation, Professor Vamivakas. The first question I have here, what implications do your resolution measurements have for astronomy?
Yeah, so I think that's a great question. And that is one of the contexts where this type of advanced scene characterization is useful. Typically in astronomy, we think of the sources that we're working with as being incoherent. And actually some of the genesis of that disagreement was whether you have a large degree of sort of coherence generated on propagation from star sources to your detector plane. I think the challenges in astronomy or in any of these problems are if you have a large number of sources, and what is what is the maximum number of parameters you could reliably take out of a scene? And I think that's still a work in progress right now.
I have two related questions here, so I'll ask you both, and hopefully you can answer them kind of at the same time. So the question says, in your mode analyzer, how is it that you set your eigenbases? And then right over here, it says, in the universal mode analyzer, does the fractional Fourier transform delay line, could it be replaced by just a normal delay line?
Yeah, both good questions. And so, yeah, admittedly, that slide is probably could be opened up into 10 or 12 slides to explain it clearly. So the first thing is the delay line, any delay line in an interferometer, all right, it implements a particular unitary transformation. So this is the math speak of it, a particular unitary transformation that has a set of eigenfunctions associated with it. And so what the interferometer does is it allows you to analyze, okay, an input beam into the eigenfunctions of that unitary transformation or that delay line. And so in a normal Michelson with a temporal delay, the eigenfunctions of that unitary are the time harmonic functions. All right, so in like a conventional Fourier transform infrared spectrometer, if you just were to kind of look at your source without putting a sample into that and take the Fourier transform of what you measure in your interferogram, what you discover are the different time harmonic functions that make up your input beam. So this is the spectrum of that source. What we've done is we've taken that temporal delay line out, and in the specific example that I talked about here, we put a different optical transformation in the fractional Fourier transform. That has the Hermann-Gauss functions as its eigen set. And so we are able to then, through a similar kind of thought process, deconstruct an input beam into the eigenbases of the fractional Fourier transform. If I was to put a different transformation in there, so another one is like the fractional Hankel transform. When you're getting into this business now, you're looking up all these different transformations, and so that allows you to work with a different eigen modes that happen to be the radial part or the radial part of the Laguerre-Gauss spaces. So I think that hit both of the questions.
Yeah, I think it did. Yeah. Okay, we have time for one last question. If we didn't get to your question, please feel free to contact Professor Vamivakas directly via email. I'm sure he'll be happy to answer anything you guys might want to know. So for the last question of the session, before we hand it back off to Professor Corkum, in slide 18, you showed that Fischer information seems to reach a peak as the separation decreases for a particular coherence case. He adds, I believe it is the case for gamma is minus 0.75. Could you tell us why that peak feature appears and what it would imply for the influence of coherence on the Fischer information? Thank you.
So that's a good eye and a good question. And to be perfectly honest, we at this point don't have a good explanation for why we get that peak for that particular case. That's an ongoing, yeah. And it's yeah. We're not sure, all the things we don't know. So we're not sure here why we get the peak. Equally kind of interesting right now for us is looking at these disks and understanding why some regions have zero Fischer information and other regions don't, and what that's telling us. We don't have really we don't have our head quite wrapped around that yet either.
Okay, I'm getting messages from mission control that I'm allowed to ask more questions and go over time. So if that's the case, I'll ask a few more questions we have here. So how would one scale these super resolution ideas to heterogeneous samples, such as those found in biology, where dispersion and scattering vary?
I didn't catch the
Ask that
very
again.
last
Did I freeze or
part
did you? I think I froze.
It
Yeah.
could have been me, but
Again, I'll ask it again. How will one scale these super resolution ideas to heterogeneous samples, such as those found in biology, where both dispersion and scattering vary spatially in a complex manner?
Yeah. So again, this is trying to implement this with, as you're asking, kind of realistic samples comes down to how well we can construct the model of what we are going to measure. What noise, like what types of noise sources, you're indicating a couple kinds of potential noise sources and trying to do this. So it really comes down to what we know, what we don't know, the model of our system. And then when we turn the crank on our estimator, are we able to sort of outperform conventional imaging approaches?
The final question I have here is very similar. How could we use these post-selection on proper mode techniques to reconstruct image of a complex object with a resolution beyond the limit? I suppose the answer is very similar.
Yeah. I mean, so I guess
seems to be a hot topic. Yeah.
Yeah. I mean, so certainly you could with the more complicated object, if you can really decompose into all of those Hermann-Gauss functions. We've only really been working with parity in our experiments. There is an opportunity to resynthesize the thing that you're looking like. You've projected along a basis, and so you just build it back up if you're able to have both the amplitude and the phase information in those coefficients. So one path would be our interferometer, like all first order interferometers, only gets, in some sense, the amplitudes of those coefficients, not the phases. So if you did some kind of like phase shifting interferometry, you could access the phases and then have a way to reconstitute. We also have done some work in the context of partially coherent object distributions, where instead of again directly trying to measure something like the cross spectral density, you could use the measurements of the mode projections to determine the moments of the given distribution that you're looking at, and then try to reconstitute the cross spectral density from knowing the moments. And that's another approach to object reconstruction that we're thinking about. So that's starting to move away from 2 points in a very constrained problem to something that's a little bit more realistic.
Okay, thanks for all of your answers and for your nice presentation, Professor Vamivakas. I'll now hand off the microphone back to Professor Corkum, who will end this session. Thank you.
So I want to take the opportunity to thank Dr. Vamivakas for a wonderful talk and very thought-provoking talk, and also Professor Steinberg for also a wonderful talk. It made this a very good session in which to end. I want to also state that this may seem like it's dominated by the University of Ottawa, but this is supported by both the University of Ottawa and the National Research Council of Canada. So you've been, well, they've sponsored both organizations have sponsored this talk, these talks. And I finally want to say that I think on the chat, you will have a link to the poster session. So please go to the posters, and the posters will be open until about 3:30, I believe, maybe 3 o'clock. So please enjoy the poster session. Thank you.